Having looked at the principles behind deep learning and the hardware and software factors that make deep learning work in the last two videos in this series, it's now time to look at the data required to drive deep learning. We've mentioned that deep learning relies on huge data sets, often referred to as big data, being fed to the GPUs that then perform the parallel processing in the framework of your choice. However, this data needs to be prepared prior to ingest into the system. Data preparation is the first stage of 4, and it's the process of readying data for the development, training, and implementation of an algorithm. It's a multi-step process that involves data collection, structuring and cleaning, feature engineering, and labeling. These steps play an important role in the overall quality of your deep learning model, as they build on each other to ensure a model performs to expectations. Once you've collected the data, preparation can begin. Data structuring is the next phase and includes organising and formatting, standardising, and dealing with any missing data. Once the data is structured properly, this allows you to cleanse it better, spotting and removing anomalies that will cause issues within your algorithm. At this point, feature engineering software may be used to define the most important information within your dataset and clarify particular relationships. Finally, data labeling is the final part of data preparation for deep learning because it specifies which parts of the data the model will learn from. There are multiple software packages available that are specifically designed to help with data cleansing, feature engineering, visualization, and data labeling. Now that we have a prepared data set, the next stage of deep learning is development. The data set is now subjected to your chosen libraries and frameworks to begin building your CNN and AI model. At this stage, it's experimental, and the CNN will involve only a few layers, as it's best to use small data sets so models can be created quickly and scrapped if they aren't what's required. This stage can be carried out on relatively low-powered hardware. Typically, 1 or 2 GPUs is sufficient. However, development workstations with 4 GPUs may enable models to be started at once, so time to develop your ideal model is reduced. Once you think you're on the right lines, the small model can then be advanced to the next stage, training. This will require a much greater hardware demand. When training a neural network, data is put into the first layer of the network, and individual neurons assign a weighting to the input. How correct or incorrect it is based on the task being performed. In an image recognition network, for example, identifying cats, the first layer might look for edges. The next might look for how these edges form shapes, rectangles or circles. The third might look for particular features such as shiny eyes and button nose. Each layer passes the image to the next until the final layer and the final output determined by the total of all those weightings is produced. The neural network gets all these training images, does its weightings, and comes to a conclusion of a cat or not. What it gets in response when the training algorithm is only right or wrong. And if the algorithm informs the neural network that it was wrong, it doesn't get informed what the right answer is. The error is propagated back through the network's layers, and it has to guess at something else. In each attempt, it must consider other attributes. In this example, attributes of catness, and weigh the attributes examined at each layer higher or lower. Then it guesses again and again and again until it has the correct weightings and gets the correct answer practically every time. It's this repeated process of hundreds or thousands of training epochs that makes this stage very compute intensive, and that's why you'll usually see systems aimed at AI training being multi-GPU servers to provide as much power as possible. To make use of all that training in the real world, you need a speedy application that can retain the learning and apply it quickly to data the model has never seen. This last stage is called inferencing. Inferencing is taking smaller batches of real-world data and quickly coming back with the same correct answer. The reason inferencing needs to be performed at speed is due to the real-time deployments it's most likely intended to be used in. If you think of an autonomous car, the trained model is much more complex than our cat or dog example, as it must be able to recognise a wide variety of objects such as cars, vans, bikes, streetlights, pedestrians and road signs. As the car drives along the road, its sensors must be able to recognise any given object and rapidly process what it is and how to react to it. There's no time or need to understand detail in the image. At the training stage, for example, pedestrians could be male, female or children. However, during inference, pedestrian is sufficiently accurate to allow the vehicle to slow down or maneuver to avoid them. Because of this downsizing, inferencing can be carried out by less powerful hardware, often a single GPU system or an edge AI device with an embedded GPU module. So now we've covered the various stages of deep learning, why not watch the next video in this series, Deep Learning Hardware?